some aspects of gravity as well. Okay, so yeah, I will divide you into few groups, maybe 4 or 5 members per group, and then I will send you the papers. You are supposed to, like last time, you were supposed to prepare a presentation, record it, and send it to me within the time frame which I will write you in the email as well. So I'll leave you with enough time so that you can do justice to the paper. But this time, please make sure that it is a coherent presentation. I don't want to see like one person's phone screen being projected where the slide style is completely different or written in Word document or something. That doesn't look good in a coherent presentation. Make sure that you all put together your efforts in preparing the presentation, and then of course all of you have to present the paper as well. Okay. So I was also reading your mid-semester feedbacks that you provided in the Shiksha portal. Uh, mm, so one of the feedbacks were of course around reading more scientific papers. So sure, I think that's a great idea, and it always was in my mind. But earlier days you were not equipped enough to read scientific papers, at least in this subject. So I did not send. But from now onwards, I will at least I'll try to send some more in the form of assignments, such papers, so that you are also equipped with you are familiarized with how a scientific paper is read and how it is to be presented. And of course, you said that you liked the presentation assignments. I think it's a good idea. It also develops few of your softer skills. For example, you can make better presentations if you do them frequently. You can present better. Your teamwork, the spirit of teamwork, also gets better. So I think it's a good idea, and we will get into it. Um, uh, there was another feedback I remember that someone wrote that yes, we are following only one book, but you want to read more scientific papers. I mean, you can always do that. You have to be a bit proactive in that sense. I mean, you have a free Science Direct, free Springer, everything given from the institute. You can search any topic, yeah, what you have been reading. There are plenty of free books on geophysics as well available online. If you follow Telford as well, along with Lowry, you are in a pretty advanced stage of learning. But I have to look for everyone in the class, so I don't want to make it as a part of the syllabus. But then it's your individual responsibility to gather more knowledge and study more advanced stuff. No one is going to stop you, and I'm always there to help you if you are taking that proactive. I mean, step by yourself. Read some papers. If you have doubts, you can always discuss with me, uh, and also more advanced books. So I leave it up to you. You are most welcome to consult with me individually if you want to um, get into more advanced stuff. But then, of course, in this assignment, you will see some scientific papers where these techniques are used. Okay. There was another feedback that I read around, you know, um, about the exam techniques, about people cheating, and so I don't exactly know what I can do about it. I expect you to be honest and answer, and I try to set up questions which are more analytical and which you cannot exactly find an answer um, in the internet or in the books, and you have to think about it. So, and I do get a good spread of marks, so I feel that you have been honest. That is what my impression is. out of the questions that you have answered honestly. Uh, you have not discussed amongst yourselves, at least not largely. So that and the distribution of the marks reveals that there was not much of copying or discussions. So that is good from me. But then we were very early in the subjects, but we don't also have a lot of questions so that we can float them around and then randomly select and stuff. But more than that, I trust your honesty. This is a special situation, and we are all trying to do our best. Uh, if you cheat, you are only cheated. That's yes. Your last presentation assignment was great. I mean, I have not put the grades as yet, but it will be graded. Yeah, it will be graded. It will be graded. But yeah, so your this presentation will also be graded. Yeah, so but don't worry too much about the grades. You can ask your earlier batches and all. I am not very strict with grades. They are I'm more lenient, and if you will not get anything less than what you deserve. Okay, so make sure that my objective, at least in this environment, that you learn more. Uh, and your concepts are clearer. Okay, so yeah, so I still trust your honesty. Please make sure, if you cheat, you are the one who gets cheated. So that's the simple thing. Anything else you have to discuss about feedbacks that you have given? These are the few points that I saw I should talk about, so I talked about them. You have anything in mind? Let me ask the departmental representative. Adil, anything else which is you think we can improve?
Hello.
Yes, Adil.
As for now, I don't think there is anything.
Okay,
Okay,
all
sir.
right. Okay, so then we start with today's class, and we are going to discuss about paleomagnetism. I'll fire up a presentation. Let's see. Okay, someone wants to say something? Unmuted. All right. So we are going to discuss about paleomagnetism today, and that's a very important topic. And make sure that you understand every bit of it. Hence, I did not want to put them in a pre-recorded video. I wanted it to be a live session so that all the concepts are clear with you. Okay. So you can imagine that there is, I mean, although it is not the case, but for all practical purposes, you can imagine that there is a big bar magnet which is sitting inside the earth, and these are the possible magnetic lines. Now, if you join the North Pole, the magnetic North Pole and the magnetic South Pole, the line that joins them is called the magnetic axis. And a line which is perpendicular to that, or actually it is not a line, it will actually be a plane, right? Because it's three-dimensional, and this is a cross section of the sphere itself. So the plane which is actually perpendicular to the magnetic axis is called magnetic equator. Okay. Now there is a difference. I mean, what essentially happens that this magnetic axis essentially wobbles around the geographic North Pole, around the geographic pole. Okay, So it kind of rotates. And the difference between the magnetic axis and the geographic axis, this the deviation is not also fixed. At the time being, it is around 11.5 degrees, but this deviation actually changes. Okay. So this is magnetic North Pole, this is magnetic South Pole, this is the magnetic equator. Magnetic equator and magnetic latitudes are similarly defined. Okay, so you can also define, latitude, which is essentially the difference, the angle. So say for example, if I have a point at this a point here, and if I extend that point, if I join that point, let me, I can, perhaps I cannot. So if I, let me just make sure. One moment. Okay. Now, say for example, if I have a point here, point P, right, and then I can join that point P with the center of the Earth, okay, and the angle that it makes with the equator. So this is, say for example, we call this angle theta. So theta is nothing but latitude, okay, and if this makes an angle lambda with the magnetic equator, lambda is called magnetic latitude. Okay? And you can see that is not exactly the same. Okay, but you know about this angle. You know about this angle. So it will be the same angle here. So you can do a transformation to actually calculate your actual latitude from the magnetic latitude. Okay, so that is as simple as that. Uh, so the Earth's magnetic field is symmetric about the magnetic axis. Now, what people have now, let's now there are two things that I want to define at this moment. Okay, one we call as the declination, and another we call as the inclination. Okay, so the Earth's magnetic field doesn't align with the Earth's rotational axis. It is presently tilted at an angle of 11.5 degree, as I said. But this 11.5 degree does change, and we will see that in the data that we are going to discuss. The magnetic North Pole differs from the geographic true north, and this difference is called declination. Okay, so this difference is called declination. Now, the Earth's magnetic field lines intersect the surface of the Earth at an angle. Okay, as you can see here, that these are my Earth's magnetic lines, and they are intersecting the surface of the Earth. Okay? At the poles, it is nearly vertical, okay? And at the equator, it is nearly horizontal. And anywhere in between, it is at an angle. And that angle is called inclination. It can be measured with a compass. So if this is the compass, as you can see, when the north arrow is actually pointing down, we call it positive. Yeah, when the north arrow essentially points down, we call it positive. When the north arrow points up, we call it negative. And you will see in the northern hemisphere, the north arrow will point down, and in the southern hemisphere, the north arrow will point up. Okay, so positive inclination refers to northern hemisphere, and negative inclination refers to southern hemisphere. Now, this is one very particular relationship that I want you to remember. Tan I is equals to 2 tan lambda. Okay, tan I is equals to 2 tan lambda. This is a very, very, very important equation on which the paleomagnetic studies are actually standing. Okay, where I is the inclination and lambda is the magnetic latitude. Okay, I is the inclination and lambda is the magnetic latitude. So, say for example, now if you take a compass and then if you are in Bhopal, you take that compass and measure the inclination and then use this equation, tan I is equals to 2 tan lambda, you will be able to find out the lambda. Okay, and from there you can essentially do that correction for your magnetic latitude to true latitude. You can find your latitude. So magnetic latitude is tan I is equals to 2 tan lambda. This is another important equation to remember. Now, another very important thing to remember is something called secular variation, and we have shown we have just said that 11.5 degree. Okay, let me just do a little bit of sketching for you. What is happening? Come on. So long. Happening. Okay, let's not waste time. Let me just draw it here itself. Let me just do a screenshot and then I can draw it. So as I was saying that uh, suppose this is my Earth, okay, and this is the Earth's rotational axis. So this is North Pole, South Pole, and this is the magnetic axis. This is the magnetic north. This is magnetic south. And we said this angle is currently 11.5 degrees. Okay. And then we said that this magnetic north pole, this magnetic axis essentially rotates. Okay, it actually rotates around the true geographic axis. And then this angle essentially changes. Okay, this angle essentially changes. So from observatory records going back few hundred years, we know that the magnetic axis continually changes its direction. This is slow and somewhat irregular. And the variation that we observe, that is what we call as secular variation because of such rotation, right? And you can see here the data for two observatories are given, one situated in London, another situated in Paris, and you can see that the declination and the inclination is continuously changing. Okay, right? So, and these are the corresponding years, starting from 1576, 1600, 13, yeah, 1796, yeah. So, like that, I think these dotted lines are actually your extrapolation, but you have real data from the solid lines: 1796, 1805, 1820, 1815, 1870, 1914. Okay, so you can see there is like a one part of this whole circle is kind of complete. And this is kind of your extrapolation. And similar for your London Observatory as well. Okay. Now, so that is what we call secular variation. It is another important thing to remember. Right. So Earth's past magnetic field. Now, so this is what we have discussed right now. Now the Earth's till its inception of the formation of the Earth, so the Earth's magnetic field has been keeping on changing. The Earth's magnetic field has been keeping on changing. The other thing that happened, that due to plate tectonics, the position of the continents have also kept on changing. Okay, so what we are going to do now, we are going to look at the uh, rocks where the rocks paleomagnetic signatures, the magnetic signatures of the during the formation of the Earth. Okay, we are going to look at them, and we are trying to see. We will try to see if we can find out its. We can find out its paleomagnetic positions. Okay, its paleolatitude. I wanted to use the whiteboard. I don't know why is it not working. Come on, why is it so slow? Now this works. Okay. So first I will take you through the slides, but before doing that, let me make you understand the whole thing with some drawings. Okay. So suppose I'm giving you a very real life example. So for example, in um, you are in Bhopal, okay, and you have found out a beautiful section of rock. I think I discussed about this in a smaller details during plate tectonics, but now we will be able to appreciate it more, I'm sure. Okay. And then, of course, this column of rock, you can see. So A, B, C, D, E. You are standing in front of it, okay, as a geologist. Okay. Now, look, knowing the law of superposition and law of horizontality, the basic laws of stratigraphy, A is oldest. Okay, so A is oldest, then B, then C, then D, then E. Okay, E is the youngest. This is my younging direction. If I am looking at a column of rock, the ones that sits in the bottom is the oldest. Okay. Now, as a geologist, what you do, you essentially collect, few samples from them. So you collect samples. But for this particular study, what you need to collect oriented samples. Oriented samples means, so for example, from this particular rock, from the bottommost rock A, you have taken a block sample. You have broken it up with your hammer. Okay, but before you break it, you have marked that in this rock, this is the north. Okay, then you will be able to automatically know this is east, this is west, this is south. Okay, And then, the plane that you have broken, yeah, this has a strike in this direction, and this has a dip in this direction. Okay, so the strike is northwest southeast, say 320 degrees, and the dip is suppose 45 degrees. Okay. So the dip is towards southwest, right? So this is an oriented sample. You mark your strike, you mark the dip, you mark the dip direction that you have measured before breaking the rock. Okay, and then you mark your north southeast trace on the rock. So this is an oriented. This is a piece of oriented sample. Now, say for example, from A you have collected 5 such samples, from B 6, from C 4. It depends on how many you can break, how many is it easily accessible, it is too hard, and so many factors, whether you are too tired, whether you want to do a quick and dirty job, whether you are really really meticulous and you want to collect more samples. More samples means better data. Okay, from D you have collected 7, from E you have collected 9. Okay? So those are the oriented samples you have collected. Okay? Now you bring that samples back to your laboratory. All your samples are oriented. Okay, and then what you do, you cut codes out of them. These codes are generally very specific in diameter and length, diameter and height. Generally, this is around 22 millimeter, and this is around 25.4 millimeter. And this is due to you are going to use them for some experiment, so they have a very particular specifications. Okay? And these codes are also oriented. That means in this code which direction is the strike direction, which is the north direction, how much this plane was dipping originally. Okay, how much this plane, how much this plane was dipping originally. What is the direction of the strike? So all these uh, codes that you have taken out from these samples are also oriented. Okay, so from each sample, perhaps you take out around 6 cores from each sample. Around 5 to 6 cores. So that means in A I have around 30 cores, and in B I have around another 30 cores. In C around I have 24 cores, and D around 35 cores, and C around 45 cores. Okay, so these are the number of cores that you have. Now you do something. So you have these cores, and then from each of these cores, now you have to find out. You remember we talked about that I have this magnetic vector, the magnetization, which is my MT, my total magnetization, which can be resolved into two values, which is MR and the other one is MI, right? MT is the total magnetization, MR is the remnant magnetization, and MI is my induced magnetization, right? So I take each core, okay? I take each core, okay? And then I demagnetize them. demagnetize them. The demagnetization can be done by two ways, and we have already discussed about the process of demagnetization. Can someone tell me, if you have been following the class properly, can someone tell me what are the two processes by which we can demagnetize this sample? Let me ask Yash, tell me, what are the processes by which I can demagnetize these samples? Yash,
Yes, sir.
yeah, what are the processes by which we can demagnetize these samples?
I'm not sure, sir.
No?
Not sure.
No, so that means you are not studying. That makes me upset. Okay, Srivats, tell me, what are the processes by which we can demagnetize them? Come on, anyone? Shivangi, you are not sure as well. Shivangi, Akriti, Amal, anyone? Prakriti, Shubham, anyone?
Yes, sir.
Yeah, how can we demagnetize these samples?
I've not studied, sir.
Very good. Am I not putting enough effort to make you understand, all of you? Disappointing. Anyway, so there are two processes by which you can demagnetize them. You remember we talked about the hysteresis loop. What we do in the hysteresis loop when we try to demagnetize. So this is the demagnetization card. This is the magnetization card. You remember this is the demagnetization card. What do? I put an alternative field, AF. I put an alternative field. So I know the magnetization vector, which way it is. So I know the MT's direction when I measure them. Okay. So I put an alternate field. So what that alternate field will do? It will try to reorient my magnetic moments and try to randomize them. Right? So one by putting alternate magnetic field. The other way, you remember we talked about, putting temperature. If you put temperature, what happens? The magnetic moments are also randomized. Okay. So thermal demagnetization, TD. Alternate field demagnetization, alternate field and thermal. Temperature dependent susceptibility curves. We discussed about them. What do you do there? You essentially demagnetize your sample. You make your magnetic moments random. Right? So So if you apply AF and if you apply TD, what I will essentially do, by each step, I will keep on decreasing this MI. Okay? I will keep on decreasing this MI. Very funny. Okay. So I will keep on decreasing this mi. If I am okay, with each step I will decrease mi. Okay, with each step of alternate field demagnetization or thermal demagnetization, and there will be a time where I will only be left with my remanent magnetization. Okay, I will only be left with my remanent magnetization. And we discussed that what is remanent magnetization? Remanent magnetization is the magnetization that was acquired by the rock during its formation, right? That was acquired by the rock during its formation. So the first step is demagnetize your sample so that you can get rid of induced magnetization. Okay? So getting rid of induced magnetization. So once you get rid of the induced magnetization, you are left with your MR, which is the remanent magnetization. Now, let us look at this remanent magnetization vector in 3 dimension. Okay? Let us look at this remanent magnetization vector in 3 dimension. I was keeping on talking. I'm sorry, I got disconnected. How much did you hear? I was keeping on talking and then I realized that I'm out of the meeting. How much did you hear? Can just someone tell me? At what point did I get disconnected? Hello? Hello? Can you hear me? Hello. Can you hear me all? Hello. Hmm. Okay. So I was talking about the demagnetization, right? So now, after you actually get rid of all your induced magnetization, okay, by alternate field demagnetization and thermal demagnetization, you are left with only MR, which is my remanent magnetization, right? And remanent magnetization is what? Remanent magnetization is the magnetization that was acquired by the rock during its formation. Okay. Now, remanent magnetization is a vector which I can put into some reference frame. So this is my Z. You can see Z positive and Z negative. Okay, Z positive and Z negative. Okay, and then what I have done. This is my horizontal plane. Horizontal planes are axis are north and east. That is what I have taken. I could have taken south and west. Doesn't really matter. Okay. Uh, and then this is my MR where it is hanging. So I have measured the MR of each individual core, right? And then I have projected my MR on the horizontal plane. Then I asked, what is this angle? This theta, the angle between the MR and its projection. What is this angle will then be called? Anyone?
Sir, inclination.
Inclination, absolutely. So this is my inclination. So let's just name it I, right? So this is my I. And then what would this angle be? The horizontal projection and the north. This angle will then be D is my declination. Okay. So from each of these codes that I have taken from each of these samples, I have got one inclination value and I have got one declination value. Right? Now let us try to look at, now we will work on this rock A. Okay. Now we will work on this rock A. And what we will do, we will plot them in a stereographic projection. Now, those who have done Earth and Environmental Science Laboratory, you must remember about stereographic projection. If not, please go back and refresh yourself what is stereographic projection. So I am looking at the equatorial plane of the stereo plot. Okay, and you remember the periphery essentially denotes so this is north, east, south, west. The periphery essentially denotes the value of trend, and the you know this division essentially denotes the plunge. Okay. Now, if I compare trend and plunge of a linear element that we have discussed in the class before with the declination and inclination, we can very well say that declination is kind of analogous to the trend, and the inclination is analogous to the plunge. Right. So, for each of these codes, okay, for each of these codes, I can plot the declination and inclination value in the stereographic projection. Okay. And if my inclination is positive, okay, then it is a lower hemispherical projection. If my inclination is negative, then it is a upper hemispherical projection. But that doesn't matter. Lower inclinations are generally denoted with a solid circle. Uh, is that true? I think the lower inclination is denoted with a hollow circle. Conventionally, it doesn't really matter. And the negative inclination, I negative. Yeah, I negative will then be, this was Z, this is east, this is north, right? So I negative means the MR will do something like this, right? And then you have to project down. Okay? So I negative is generally plotted like this. And we said I positive means northern hemisphere and I negative means southern hemisphere. Okay. So for each of these codes, what I will get an inclination and declination value, which I will plot here. So how many codes did we say for A? We had 30 codes, right? So they are these same rocks, so I expect them to be plotting at the same point. But if we do it practically, what I will observe, I will find very close. I negative, we said they will be solid circle, na? So solid circle. They will be plotted very close. They'll cluster at a place. Okay, these 30 points, the inclination and declination. Now, if this rock would have formed at the same time, I should ideally get, a single point. But why am I getting this cluster of points? This is because of the secular variation. This clustering is because of secular variation. Maybe this rock actually took 10 million years to form, right? Within that 10 million years or 1 million years to form. Within that 1 million year, actually, Earth's magnetic field also did not stay constant, right? Earth's magnetic field actually wobbled. So rather than getting a single point, I am getting a cluster. Okay. Now, how would you know that? Now you have got that. Now, when you have got that, what you will do? You will actually calculate a mean out of it. Okay. You will calculate a mean out of it, considering a 2 sigma radius. I hope you know what 2 sigma standard deviation is. 2 sigma standard deviation or alpha 95 standard deviation. You will calculate a mean of this data. Okay. So, and then you will find a mean inclination and declination for A. Okay. A mean inclination and declination for A. Okay. Now what I will do?
Excuse me, sir.
Yeah.
Sir, just for clarification, positive inclination means I'm in this southern hemisphere.
Positive inclination means you are in the northern hemisphere.
Okay.
When it is pointing down.
Okay.
Okay. And negative
Yes.
inclination means it is pointing up. Yeah. And that means you are in the southern hemisphere.
Okay.
Okay. So now, for each of these A, B, C, D, E, in all these layers, I will find a mean declination. I will find out a mean declination and a mean inclination. So DA, IA, DB, IB, DC, IC, DD, ID, DF, IF. Now, for the time being, let us not be bothered about the declination values. Let us only look at the inclination values. Okay, so this is what we are looking at. Now, what I will do, my next step, I'll use this formula. Tan I is equals to 2 tan lambda. Okay, and then I will find out the magnetic latitude for each of them. So lambda A, lambda B, lambda C, lambda D, lambda E. Okay? And then I will do a little more correction, and from them I can actually calculate lambda AT, that is my true latitude, lambda BT, lambda CT, lambda DT, lambda E. It will not be perfect because we don't exactly have the what exactly was the difference between the magnetic axis and the true axis all the time, but then we have a pretty good idea. So you can use a standard transformation and you can calculate that problem. But it's enough to actually calculate your, for the time being, just your magnetic latitude. Now, if you have calculated your magnetic latitudes, and if you see that lambda A is different than lambda B, and lambda C, then lambda D, and lambda E, what does that mean? That means that, so you have taken it from Bhopal. So Bhopal is currently, now if I look at it, this is equator, okay? This is 23.5. This is the Tropic of Cancer. So Bhopal is right now very close to 23.5, right? If you go to from Bhopal to Sanchi, you will see the Tropic of Cancer. So we can say, average it out, that Bhopal is kind of at 23.5. Okay. Now I have taken this rock section and I see my lambda A is lying here, lambda B is lying here, lambda C is lying here, lambda D is lying here, lambda E is lying here. Okay, and I, so my, for example, of course, I did a little bit of mistake. This Bhopal should be on the same longitude. Remember, from this type of, so far what I have discussed, we cannot do anything with the longitude. Okay, so we have to plot these points on the same longitude that we are currently in. Okay, so this is my longitude on which currently Bhopal is, which you can find out from Google, some 73 or 77 degrees. I don't exactly remember, whatever it is. Okay? So a particular longitude on which you can actually put your, this is where Bhopal is currently now, and you can actually have plotted the, so these are what we call as the paleolatitudes. Paleolatitude. Okay, these will be called paleolatitudes. So what that means that Bhopal was not always here. While A was formed, this rock A was formed, Bhopal was here. When B was formed, Bhopal was here. When C was formed, Bhopal was here. When D was formed, Bhopal was here. When E was formed, Bhopal was here. Now, interestingly, you can see between, this is A, B, C, and D, So till A, B, and C, I should expect to have the magnetic inclination to be indicative of southern hemisphere, right? That means I will have a negative inclination. But at D, I'll see my inclination will change to positive. At E, and then it will continue. Okay, so my inclination changes. So that means the continent essentially, which is carrying Bhopal, there is my Indian continent in this particular case, actually has jumped from the southern hemisphere to the northern hemisphere. So this is how you calculate paleolatitude. Okay, I will continue with the discussion further how to use these paleolatitudes and calculate virtual geomagnetic pole and calculate apparent polar wander path in the next class. But let me see if you have any question. Was it clear? How is this done? Simple, you go to the field, you collect oriented samples. From these oriented samples, you make cores. From these cores, you actually first do demagnetization. So demagnetization is done by two processes. One is called thermal demagnetization. The other one is called alternative field demagnetization. When you subject them to the demagnetization, what you do? At each step, you keep on decreasing the induced magnetization vector. So then you are left with only the remnant magnetization. Remnant magnetization is nothing but the magnetization that was acquired by the rock during its formation. And then that magnetic, the magnetization vector essentially will have an inclination value and a declination value. If the inclination is positive, that means you are in the northern hemisphere. If the inclination is negative, that means you are in the southern hemisphere. And then from there, uh, you calculate the inclination from the inclination, and you can use tan I is equals to tan lambda. You can calculate the magnetic latitude, and from magnetic latitude with some transformation, you can also calculate the true latitude. Okay? And then if you find within that pile of rock, which were formed at different times, the one which is sitting at the bottom being the oldest, and the one sitting at the top being the youngest, and they form in different, they show different paleolatitudes. That means that the continent which is carrying that rock were also not stationary. They moved during, they moved during the formation of those rocks A, B, C, D, and E, and kept on acquiring the magnetization while it was traveling. Okay, that is how you calculate paleolatitude from the paleomagnetic data. Anything you want to, you have not understood, it's the time to speak up.
Hello.
Yes, Adil.
Sir, can you explain the part where, how do we demagnetize? Let's say I'm using the alternative field to
Yeah,
demagnetize my sample.
right,
So all we have for now is the total magnetization.
right, absolutely.
So how do we know the amount of alternative field that we need to apply to get the remanent
That's a
magnetization?
that's a very good question. Okay, so what you essentially see that the induced magnetization. So you can do your paleomagnetic work where the induced magnetization is not very huge. So the induced magnetization, you remember we talked about three scenarios. The induced magnetization is considerably less than the remanent magnetization. Okay, so what you will, and of course the induced magnetization will be of a different nature, right? That will have a different inclination and declination. Okay? So what you will observe while you demagnetize your sample, your inclination and declination will keep on changing, keep on changing, keep on changing, and there will be a moment after which it will not change, it will stay constant. Okay, so while it was keep on changing, that means, and it was unstable, your inclination and declination was keeping unstable. Okay, That means you are still removing your induced magnetization. And as soon as it starts to take a plateau, I mean, you keep on demagnetizing, but then still the inclination and declination is not changing. So that means you have reached your remnant magnetization. So that is how you know. So at each step of your demagnetization, you also measure inclination and declination. That's a very good question. Yeah, that's how we know.
Okay, thank you, sir.
Anything else? Okay, so we stop it here. But before I go, I seriously, honestly urge you, please, please, please study. Otherwise, these things will, you will not get a chance again in your 5 years course to study geophysics. And these are very, very important stuff, not only for your learning, but also for the exams that you are about to sit in your life, right? So it really matters whether you like geophysics or not. These are the things which will be asked your questions upon. Okay, so please make sure whenever otherwise you will fall behind. It's not about passing the exams all the time, it's about understanding the subject. Okay, so please make sure all of you uh, that you at least refresh, go back and read from Lowry's book, listen to the video once more, spend an hour every day on the subject. Okay, please do so, so that we all are in the same page. Okay, thank you very much. I'll see you tomorrow. And then tomorrow also I will, because I have not finished all the stuff today, because there will be papers on paleomagnetism. So I'll finish the lecture tomorrow on paleomagnetism, and then I'll send you the papers and the assignment. Thank you.